Yes, I'm going to talk about two topics that I've been thinking about over the last few years, tensors and sketching, and in particular, I'm going to talk about an important sketching approach to estimating low-rank tensors. And this is joint work with Anru Zhang, who's a colleague at UW-Madison, Yuetian Luo, who's a grad student at UW-Madison, and Ming Yuan, who's in the statistics department at Columbia. Okay, so the main topic of the talk, like tensors or multi-way arrays, they're becoming more and more prevalent in many settings in machine learning and data science for a number of different reasons. I suppose the most natural reason is that multi-way data is arising more and more frequently. So, for example, like 3D images are arising very commonly. For example, in neuroimaging, hyperspectral imaging, and we're going to see an example of a 3D imaging application right at the end. And then in other applications like microbiology or text mining, you can imagine that features are now kind of going across many more than just 2 dimensions, and so you're getting multi-way or tensor data of order 3 or more. And so the tensor data is arising more and more frequently. And another kind of probably where tensors are also arising more and more is in algorithms. So even if your data is originally in the form of a vector or matrix, many algorithms are kind of using kind of higher order information. So you can imagine that second moments or variances are typically matrices, but many algorithms are kind of going to higher order moments like third order, fourth order, and so on. And these are typically represented as tensors. So, for example, in higher order interaction pursuit, the index model, Markov processes, topic modeling, and many other algorithms, tensors, or you often store your data as a tensor before you run the algorithm. So both in terms of tensors appearing as multi-way data and being used as inputs to algorithms are making kind of tensors a more and more popular area of study. Okay, so tensors naturally present a number of new challenges that go beyond vectors or matrices. So, I mean, in an ideal world, if we're presented with multi-way or tensor data, we don't want to just kind of vectorize or matricize things and then sort of deal with that. We'd ideally like to preserve some kind of the tensor structure. And so that presents a number of new challenges, and I'll talk about some of those today. So in particular, probably the biggest challenge is that there's no nice notion of low rank in a tensor like there is for matrices. I'll talk about a couple of notions later, and we'll stick to one. Probably the biggest challenge, and one that I'll kind of address in the most detail today, is computational challenges. Like there's a number of because you've got like higher order data, typically the number of parameters are large, and these present a number of computational challenges. And then also like just a lot of tensor algebra just does not naturally follow from matrices. And so there's technical challenges associated with that. So there's a number of challenges in going from kind of matrices to tensors that mean you can't just kind of naturally go from one to the other. Okay, so I'm going to stick to one particular model, I guess the most standard model in statistics, which is kind of the linear regression model. So here we've got the linear regression model, but our parameter of interest is a tensor. So here, everything I say kind of applies to higher order tensors, but because the sort of notation gets kind of heavy for tensors, I'm going to just stick with n equals 3 throughout the talk. So we can imagine that our parameter of interest is an order 3 tensor, and then we sort of take an inner product of that with an order 3 tensor for the covariates. So you can imagine that being kind of a 3D image or any other kind of order 3 feature that you have. And then your response is, or output is a y, and your goal is the very standard statistical goal of using your data to estimate this tensor A. But I guess what makes it sort of very statistical is we assume this linear model. And so, we consider the setting where we're high dimensional, so the number of samples is kind of small relative to the number of parameters, which in this case is the product P1, P2, P3. And I'll kind of later go, like right at the end, focus on an example where it ends on the order of 1,000. And if you look at the product of the 3 orders, you get in the order of millions. And so as we know in high dimensional statistics, you can't really do anything unless you place some form of low dimensional structure. And so we're going to do that by placing some notion of low rank structure on A. Okay, and so as I mentioned, there's no sort of one natural notion of low rank structure, but I guess there's a couple that are widely used. So in particular, one natural notion is the CP decomposition, where you can imagine that you have, like, if you've got an order 3 tensor, you can it's a natural extension of the SVD, where you just kind of have your 3 singular vectors that you kind of take the Kronecker product of to get your tensor. But in that case, you don't, for the CP decomposition, you don't naturally get a notion of orthogonality, and the interpretation of what the rank is kind of odd. And then the other notion, and the one that I'll focus on today, is this notion of a Tucker decomposition, where rather than having singular values, you have what's called a core tensor, which is typically a much lower dimension than the higher order tensors. So the Tucker rank here is in 3 directions: R1, R2, R3, which is the dimension of the core tensor, and there's this natural notion of that relates the CP rank and the Tucker rank, and I'll talk a little bit more about the Tucker rank as we go along, if it seems a little mysterious at this point. So one natural notion that's also very connected to the notion of Tucker rank and Tucker decomposition, and this concept will come up a lot today, is this notion of matricization or unfolding. So matrices are a lot easier to think about than tensors. So you can imagine that if you have an order 3 tensor, you can kind of unfold it into a matrix, or an order 2 tensor. You can do that in a number of different ways. So this is kind of one way to unfold it. So if you have an P1 by P2 by P3 tensor, you can unfold it as a P1 by P2 P3 matrix, and you'd do the same thing for P2 by P1 P3 and P3 by P1 P2. So there's kind of three natural notions of ways you can matricize this. And the nice thing about that is it also connects naturally to the Tucker rank and the Tucker decomposition, because the ranks correspond to the rank of the matricization, and the left singular matrix also kind of correspond to these A matrices here, which is why you kind of you get the nice property of orthogonalization that you or orthonormal matrices that you don't get with the CP decomposition. Okay, so that's the notion of rank that we'll stick to today. Okay, so as you can imagine, there's a number of prior approaches to trying to estimate low-rank tensors, and they all seem to run into kind of computational and statistical challenges. So we've already heard a number of talks about regularization. So convex regularization approaches have certainly been tried. The ones that kind of typically, and this is kind of a very brief overview of the literature, but there's ones that kind of try to take notions of matricizations and extensions of matrix approaches, and these are typically computable to some degree, but not really statistically optimal, because you're kind of ignoring tensor information. There is a notion of a tensor nuclear norm that you can use, but that is totally not computable at all. And so that so that it kind of is like it just doesn't work up front. There are other algorithms that are certainly implementable. So predicted gradient descent, which is one we'll compare to today, that is not statistically optimal. And then from a computational point of view, it's not bad, but it does require evaluation of a gradient at each step, and we'll show that that's something that we don't need here. And then there's other notions which are extensions from matrix approaches, which have both statistical and computational challenges. In particular, there's nothing really proven about whether this is statistically optimal or not. And there's challenges with evaluating the full likelihood for alternating gradient descent. And I also mentioned that a number of things that you can do for matrices, like thresholding singular values, you can't really do very easily for tensors. So a lot of these approaches kind of run into challenges, and we'll compare it to some of these right at the end. Okay, so the other kind of aspect of the talk that comes in is this notion of sketching. And so there's a very, very large literature on randomized sketching, and so I've kind of given some citations, but I apologize that many other people have worked in this, and I have not done a full survey here. So there's a number of different works on sketching for vectors, matrices, and tensors. So just to very quickly introduce kind of the simplest notion of sketching, I think, is the goal is to try to estimate a vector. You can imagine that you just essentially project or subsample your data into something lower dimensional. So here, typically, these matrices U or omega are like R by N matrices, where R is much smaller than N. And so you project to a much lower dimensional space and then do your computation there. So you have a lot of nice computational advantages, both in terms of kind of storage and computation. But what's kind of been shown in this case, particularly from a statistical point of view, is this is highly statistically suboptimal, particularly in this case. And in other works on sketching for matrices and tensors, in general, they're not statistically optimal. And even though they have pretty nice guarantees in other respects, like if you look at approximation error and other things, they work pretty well. But if you consider the statistical setup that we're in here and the metrics that we're looking at, where we're really interested in a true model with a true parameter, these are all kind of statistically suboptimal. And kind of the main, I'm oversimplifying here, but the main reason for that is that the way that we're doing sketching here is we're effectively just doing subsampling, which is throwing away most of your data, which from a statistical point of view isn't going to really make your life better. And that's why kind of these approaches, although they have some nice properties in other respects, are not really suited to doing well statistically. Okay, so the key idea that we're going to use here is instead of doing randomized sketching, which is, as I said, it's very hard, we don't seem to be getting statistically good performance a lot of the time, is we're going to, one way to think about our procedure is that we're going to do importance sketching instead. So in a nutshell, we're trying to kind of sketch and import in directions that are important, that kind of capture the low rank structure, so that we get good statistical performance along with the computational advantage that we have. So in summary, and this will hopefully become clearer when I go through the procedure, some key differences between other kind of classical randomized sketching approaches. We incorporate information about why the response, which actually provides structural information on the parameter of interest, and that's why we're hopefully going to do better. And then rather than sketching in the direction of this along the samples, we're going to sketch along the parameters. And so the concept of regularization has been talked a lot. So ideally, we want our sketching to act as a regularization rather than as a subsampling. And that's exactly what we're going to achieve here. So we're going to introduce an approach where we do importance sketching, so the sketching really behaves as a regularizer. And so therefore, we kind of get, hopefully, the computational advantages of sketching, that both the storage and the computational cost advantages that we get. And then we get statistical performance that we kind of show as optimal under these low rank assumptions. Okay, so to summarize what I'll talk about for the remainder of the talk, I'll spend a fair bit of time just talking about the algorithm. So just kind of giving some the steps of the algorithm and then some insights about it, in particular the computational considerations and advantages to our algorithm. And then I'll talk about the statistical performance and show optimality in some sense. And then I'll kind of demonstrate the advantages of our algorithms over some of the existing approaches I talked about through simulations. And then I'll finish with a real 3D imaging example. Okay, so I'm going to talk about the procedure. So the way I'm going to talk about it is first to just talk about each step of the procedure in some detail, and then just give an overview, and then just try to give some intuition about it as I go along. So recall again that the model in the data is as follows. This is a standard linear regression model, and we assume that our parameter of interest is this tensor A that has low Tucker rank. So the Tucker ranks are defined as R1, R2, R3, and our goal is to estimate this from our data. Okay, so the first step is we want to do importance sketching, so we kind of have to find which directions we should be sketching in. So this is the first key step of the algorithm. And so what we're doing first is, as I mentioned, we're incorporating information about y. So what we have here is that obviously our goal is to estimate the true parameter A. What we're doing here is that kind of getting an estimate or some sort of simple approximation to that by just doing y times the the covariance tensor and then just averaging them. And this, under some conditions, gives a pretty good approximation to the A. And then we want to do basically come up with an algorithm that can give a good Tucker decomposition of this particular A tilde, which is an estimate of A. So there are a number of algorithms, but the one that we use that we think works pretty well is this notion of the higher order orthogonal iterations. And so it kind of spits out the Tucker decomposition. I'll talk a little bit more about this shortly. And so then we get essentially these low dimensional representations. So these matrices U1, U2, U3, and then these other matrices which are related to the core tensor. Okay, and so just to talk a little bit about this HOI, so this higher order orthogonal iteration. So one way to think about it is, it was an algorithm developed in 2000, and so you can think about it as an analog for higher order tensors. So for those of you familiar with the power iterations method, this is kind of a generalization of the power iterations method. And the other sort of nice thing about it is that we can actually show that it has pretty good, you can develop a statistical framework for it to show that it performs pretty well. But you could certainly replace it with something else as long as you can get a good Tucker decomposition. So again, just to talk a little bit about this and to relate it to matrices, which is a little bit potentially more intuitive. So as I mentioned, the Tucker decomposition is very closely related to matricization. So you can imagine that there's 3 different matricizations that you take. And then you take kind of the singular vector matrices for each of these 3 different matricizations, and those will be used as the sketching directions. So they're related to the Tucker decomposition. Okay, so the next thing is where we actually develop our sketches of the data. So the first step was getting the right sketching directions through these U matrices and W matrices. And so now we're going to take our original full data and essentially just multiply or get the directions that we're really interested in through these U and W matrices. So in particular, we get something like a sort of a core tensor type of representation for our x's. And then we also get something like these sort of arms, so these green, red, and blue arms through the U's and the W's. And the idea is these are much lower dimensional than our original tensor. So you imagine that your tensor has these P1, P2, and P3. We're only really getting a sketch of that and representing that in our as a representation of our x. Okay, and then another way to think about it from a statistical modeling point of view is that we can essentially just represent our original regression model and decompose it in terms of kind of these low dimensional representations. So B tilde, D1 tilde, D2 tilde, and D3 tilde. B is the core, and then D1, D2, D3 are kind of the arms of these of this tensor. And then we essentially we can represent it in this way with this additional term in the noise. So you can see that the noise has changed a little bit due to the orthogonal projection of the U's. So it's very critical that we have a low rank assumption here to make sure that the noise doesn't blow up. So essentially gamma tilde can be viewed as a sketch of A. And so the next step's very natural. We just essentially do regression, but now in the reduced dimension. So we've got our sketches of the data through this kind of core tensor, and then D1, D2, and D3 are like the arms of this. And so our original dimension was P1, P2, P3, and we've got a much smaller dimension now by doing this, by applying this sketching approach. And so the outcome is just whatever we get from regression when we do this. Okay, and then we've kind of projected things down to a low dimension with this gamma hat, which is now much lower dimensional than the original tensor. And so we kind of have to project back out to the full 3D tensor. And so the way we do that is there was a scheme developed by my co-author Anru, which is for tensor completion, where you can think of this as an analog of a higher order Schur complement formula. So for a Schur complement from matrices, you can imagine that if you have kind of the top corner and the bottom, like the two arms, that you can fill in the rest with using kind of the Schur complement formula. And so there's an analog for tensors here that was developed. And so that allows us to kind of develop, to get this final estimate A hat. And this inverse looks a little scary, but it's not, because both the B hat K and the V tilde K are low dimensional, so they only depend on R. So this inverse is not difficult to compute computationally. Okay, so just to summarize the algorithm, so the first thing we do is we're doing importance sketching, so we're deciding which directions to sketch, and this is where we use that HOI algorithm. And then we do our sketching, where we take our original data and kind of do these tensor operations to get our sketched data. Then we do our regression in the reduced dimension, and then we assemble the final estimate using this kind of cross scheme, which can be viewed as embedding from the low dimensional to the high dimensional space. Okay, so just to sort of take a step back and kind of give a different perspective of this algorithm. So if you don't think about tensors at all, there's a very simple way to think about this algorithm, which applies to kind of any sort of high dimensional statistics problem when you have low dimensional structure. So essentially the first step is to just find the right sketching directions, or find a projection. So in particular, you take an average like this of x and y to get your A tilde, and then you define some projection operator. So we project to a low dimensional space, and ideally this projection captures the low dimensional structure. Then you do your regression or whatever other procedure you want to do, whether it's like regularized or logistic regression or anything else in that low dimensional space. And then you do your embedding or your inverse projection to project back out. So that's all that's really going on. And in fact, if you want to think about something concrete, like kind of the most simple high dimensional statistics problem is sparse vectors. Like that falls into this framework very nicely, where essentially the projection is just thresholding, taking the top M values, and then the embedding is just kind of filling in all the other entries with 0. And so this actually corresponds to a procedure that was developed back in 2008, the Schur independent screening procedure. But as we see for tensors, there's a bit more work, because for the projection here, we need to come up with a way to do Tucker decomposition, and we use HOI for that. And then we have to do the embedding as well. So that's sort of where the main work lies. So if you kind of want to compare and contrast this with Schur independent screening, they fit into the same framework. The only difference is the projection and the inverse projection steps. So you can imagine that if you have a high dimensional problem with low dimensional structure, you can do something like this, and provided you can come up with a computable projection and a computable inverse projection or embedding, you can kind of do this procedure kind of can be extended. Yep.
Can you ask what are the properties that you need for you're using HOI? Like what properties do you need, in particular would quasi-optimality be enough?
So the question is, what properties of the projection and inverse projection would you need? And you said something about quasi-optimality. What do you mean by that?
So quasi-optimality is within some constant factor of the best possible Tucker rank K decomposition.
Right.
And so that's achievable by a lot of algorithms that are much more efficient.
Right. Yeah, so it's a good question. So we use HOI because that we can show is statistically optimal. If it's quasi-optimal, I'm not sure if that's enough. We'd have to kind of check that out from a statistical point of view. But certainly from a computational point of view, there's nothing stopping you from using anything else, as long as you can then, and then doing the inverse, I guess we could just use the same scheme we have. Yeah, but I certainly think you could use other approaches other than HOI for that. Yeah.
I noticed even HOI doesn't get the optimal, right? Because
it doesn't get the optimal, but it seems to do well. But I mean that's sort of a good open question to think about. Yeah. Okay, so now I'll talk a little bit about the computation and implementation aspects of this. Just sort of summarizing what we've talked about. So one other nice aspect of this is that we only have to access the true data twice. So like if you don't want to store your data in RAM, you instead kind of want to store it in a hard disk, you can actually just access the real data twice, and then you don't have to, then you're saving a lot in terms of memory. So you potentially get much bigger savings over other methods, for example, that require computation of the gradient at each step. And so, in particular, if we look at both the memory requirements and the computational complexity, we're doing pretty well. So for memory, we get this order of p cubed. So the p cubed comes from storing this a tilde. But then we don't have to store like n times p cubed, which is what the original size of the data is. We just need the sketches, which is n times pr by r cubed, so plus r cubed. So this is sort of for the sketch data. And so this is actually quite a big saving potentially. And then from a computational point of view, we're also doing reasonably well because there's the computational cost of HOI, which is t times p to the fourth, and maybe there are faster methods there as well. And then there's the computational complexity of the regressions, which are not too bad, and you can show that they're significantly better than other methods, and I'll do a simulation comparison later as well. Okay, so in addition to that, and one other aspect of this we use is this naturally allows you to do your computing in parallel because you only access the data twice, and the only computations you do are first an average and then a regression. So these are things you can easily do in parallel. So if you have B machines to distribute across, like your computation and storage costs in terms of n goes down by a factor of B. So we will show that you can kind of distribute this, which can speed things up a lot as well. Okay, so one of the things I mentioned was that theoretically this algorithm performs really well. So I'll give kind of a summary of our theoretical results here. So this result doesn't require any assumptions on our x's or our epsilons. It's kind of a general result on how well our estimate does in terms of the L2 or Hilbert-Schmidt error. And so what is significant here is that if you just did ordinary linear regression, the term you would get is just that x transpose x inverse times x transpose epsilon. But what we get here is we get like x tilde is the reduced data, and epsilon tilde is this new noise, this kind of new noise term here. And so we get everything in terms of these lower dimensional terms, which is what's kind of nice. So rather than having x, we have this x tilde, which ideally would get things to be, in practice, should hopefully be lower, and we'll see that that's the case for a number of under certain assumptions on our design matrix. And the other kind of key point is that we have to hope that have to assume that our sketches are pretty good. If they're not good, then we're kind of in trouble. And so we have these quantities theta and rho that are essentially a measure of how well we're doing in terms of our sketching. So we're ideally getting like things in terms of this lower dimension, like this reduced least squares problem, rather than the original least squares problem, as long as we get good performance in terms of sketching. And so there's a number of steps in the proof, but just to try to give a bit of a flavor of the steps involved, it's to do with the fact that, as I mentioned earlier, you can rewrite the model in terms of this dimension-reduced regression. So you can rewrite the y's in terms of the low-dimensional representation with these x tildes, and then I think that should not be a plus there. That should be a times, sorry. But that then this kind of new noise term, and then you can kind of, as with all things in tensors, usually decompose into many different directions, and we do that across the different projection matrices, and then this rho comes from kind of a bound that we developed for the cross scheme. So that comes from how well does that cross scheme, which puts things back together, how well does that perform? Okay, and so from a statistical point of view, we usually like to see sort of n's and p's and m's in there, and so we've got this is what we have, and we make some assumptions about IAD Gaussian design here, and so we assume that both our noise and our data come from IAD Gaussian entries. So there's a lot of terms here, but you can kind of look at this m over n term here. So m is really the low dimension. So m is this R1, R2, R3 plus this other term, which is the low dimension. And then you have other terms that kind of depend on the lowest singular, making sure the lowest singular value is not too small, and various other quantities that, that once these are satisfied, we get something of the order of m over n, where m is this low dimension. And the other thing is that there's, for the various concentration bounds to hold, we need n to be of the order of p to the 3 over 2 times r, which is better than other analyses on this, but this may be an artifact of the theory. The other thing that's nice is that we can show that this is minimax optimal, and we can actually show that it's also minimax optimal in terms of the constants as well. So because essentially what we're doing is just showing that we can re-express the original tensor regression problem as a reduced dimension problem, you can use a Bayes risk type argument to actually get constants that are optimal for the lower bound, and you can actually show that this under certain assumptions on the the minimum singular value and so on, you can actually show that our procedure is tight in terms of both the rate and in terms of the constant. So just to kind of summarize what we have here, under these sort of IAD Gaussian assumptions, we can show that our mean squared error sort of scales as m over n times sigma squared times this 1 plus O of 1 term. And so as far as we know, this is the first work that gives you sharp constants as well as the optimal rate. And you get, if you assume additional sparsity assumptions on your singular vectors, you can also extend this result where you'd get extra terms that involve the sparsity. And so this certainly extends to that case as well. Okay, so now just to sort of show how our algorithm performs compared to other sort of state-of-the-art methods in simulations. So I'll consider 3 different regimes, like P reasonably small, P starting to get bigger, and then P very big, just because that'll kind of include various of the other alternative algorithms that I talked about. So I mentioned projected gradient descent, and then the other algorithm, the other approach, due to Liu and others from 2013, is a convex regularization approach. So there they use an ADMM SDP type approach, which sort of works okay. And this is referred to as and then the alternating gradient descent approach. So we can see that so on your left-hand side is the mean squared error, and on the right-hand side is the running time. So we can see that in terms of mean squared error, we're kind of doing okay. This is p equals 10, so we're not getting that big here. R is 3, and this is all for order 3 tensors. We're doing reasonably well compared to other methods in terms of mean squared error. We're doing a lot better in terms of computation. And here we're probably not seeing the full advantage because p is still relatively small. When we start to go up to p equals 50, which is kind of when you do 50 to the power of 3, that's kind of significantly bigger. That rules out 2 of the other methods because they're kind of too slow to run. And so we compare only to the projected gradient descent approach here. And once again, we're doing almost as well in terms of mean squared error with the sketching approach, but we're doing a lot better in terms of computation here. So the black lines here, sorry, are our procedure, and the red lines are the other procedure. And so we're doing a lot better here. And then, as I mentioned, if you wanted to go up to p to about 400, then that rules everything else out because it's kind of it just can't run when you have 400 cubed parameters. But if you parallelize it the way that we described, you can see that the mean squared error does okay, and then our running times also kind of increases in not too terrible a way as p increases from 100 to 400. So this kind of allows us to potentially go to data sets that had not really been addressed before because existing algorithms weren't able to kind of go to that size. And so just to show that with a real data example here, so this is kind of a toy example that people use for, so this is ADHD data based on MRI images. So ADHD is a disease, and we're doing the classification problem of whether someone has the disease or not. And we have, this is from the Neuro Bureau website. And so here we have 930 subjects. And then for each subject, we have an MRI image of 3D MRI image of 120 by 145 by 121, and 356 people are diagnosed with ADHD and 534 not, and so our goal is classification. So this had been attempted in prior work in 2013 using that Tucker regression, which is the alternating gradient descent approach that I mentioned. But as I mentioned, there's no way it can scale to this size. So what they do instead is they do a discrete cosine transformation to reduce the data and then apply their algorithm. So we're kind of applying our algorithm to the original data where they have to do this kind of dimension reduction first to reduce the size of the tensor and then apply their algorithm. And so you can kind of see that, I mean, I don't think these results are necessarily great to get an accuracy here is just the number that you get right. So about 0.68, which is not necessarily great, but it's still doing better than the Tucker regression approach, and its running time is significantly better. But I think probably the biggest takeaway is that this is a fully data-driven approach, and we don't need to reduce the size of the tensors. So, and it has superior performance in terms of both accuracy and runtime. Okay, so in conclusion, so we've developed this procedure that can do estimation of low-ranked tensors, and as I mentioned, if we have some additional sparsity assumptions on our singular vectors, we can still prove something similar. And as I mentioned, we can replace HOI. So if we wanted to incorporate sparsity, you can replace HOI by this algorithm called stat-SVD, and then where you might naturally think you replace the regular least squares algorithm with the group lasso. And then there's a number of open issues. So one of the reasons I gave that sort of sketching perspective of it was that really it boils down to coming up with a good projection and a good inverse projection or embedding. And so we sort of naturally expect that this can be applied to many other settings beyond just low-ranked tensor regression. So in particular for tensor completion, that's another sort of area. And then if you have algorithms that use higher order tensors like higher order interaction pursuit or other tensor applications, those are kind of certainly open things to be investigated. All right, thanks.